Today we are going to learn about natural language processing NLP, and this video is for only those who is really want to understand or learn how a machine understand the natural language and how a human can communicate with machine. So first we need to understand what is NLP. Natural language processing is a field of artificial intelligence that enables computers to understand, interpret, and generate human language. It is important because it helps machines interact with people through text or speech, powering applications like chatbots, translation systems, voice assistants, sentiment analysis, and search engines, and improving communication between humans and computers. That is why NLP is really important for us because machine only can understand the numbers, and natural language processing it's just to create a bridge between the natural language and the numbers. And just what we need to do, just we need to apply some logics to convert the sentences, words, characters into the matrices of numbers, vectors, so that machine can understand. Let's go ahead. So first step is tokenization, and tokenization creates the foundational vocabulary for models. So first let's understand what is tokenization. Tokenization divides input text into smaller manageable units like words, subwords, or characters. Because with help of the tokenization we can create a list of strings. For example, if we have prompt tuning is fun for me, then with help of the tokenization I will break this sentence into the multiple words of list, like, and I can provide a id. Once I tokenize any sentences, in that case I'll provide some ids to the tokens. And and tokenization optimize computational resources and standardize the format for machine learning algorithms, and that is why tokenization is important. In the traditional machine learning or traditional NLP approach only relied on the white space and the language specific punctuation rules to separate words. It means if we want to tokenize a sentence, then we have some rules, and rules strongly based on the punctuation and the white space. But in other language, and the let's see the limitations. And what limitation says, it struggles with language lacking clear word boundaries or complex morphologies. It means it completely depends on the language, and in different languages there are different punctuations, and some languages there are no white spaces. Then it is really difficult to tokenize a sentence into the words, list of words, right? And sometimes we are getting the out of vocabulary error. Let's suppose if a word comes across in our processing like guac bomb, then we can't recognize these words as a separate token, leads to massive sparse vocabularies and stuff. Like if we have the word like hello world, then it can present hello and the world in the different manner in different sentences though. So we can provide this to this aid. But guac bomb, it is really an exceptional word, and it will not repeating in other sentences, and that's why it can create a sparse matrix, and that is not efficient if we are going to process guac bomb. So it will create or generate a out of vocabulary error. To resolve and mitigate these problems, we have some algorithms which is being used by our LLMs, current LLMs. Let's go ahead and see in the next slide. So byte pair encoding balances characters and whole words. So BPE is algorithm that is being utilized by LLM standard LLMs like GPT, Claude, and BERT. And let's see how it works. So BP, what it does, like it breaks a whole word into the multiple words. Like if we have a word unbelievable, then it breaks it down into three words: unbelieve and able. That's how it works. It compresses and finds the recognizable subwords into a words. That is how it works, and it resolves the OOV problem. Rare or unseen words are simply broken down into smaller and recognizable subwords. Tokens allowing models to compose and meaning from known fragments rather than falling on unknown inputs. You can see it here. Okay, and let's move ahead and see the stemming. How stemming and what is stemming? So stemming is a process to chop down a word into the root word. It is trying to convert a word into the root word by chopping the suffix of the word. Let's suppose if we have running, runs, runner, it chop it down and removing the ing, s and ner from the word and find convert it into the root word. Okay, for example, history to history, right? Let's see, stemming applies predefined hard-coded rules like removing the ing or ed to strip words to their root form. And what is the benefit of the stemming? It is exceptionally fast and reduce vocabulary size, making it ideal for classical research engine and sparse IDF models. And if we talk about the drawback of the stemming, because it blindly chop it down a word and find it the root word, and sometimes it will not effective because it blinds chops of ending without checking the dictionary, frequently resulting in unnatural non words that destroy contextual nuance. So mitigate this kind of problems, one more approach that is called as lemmatization. Let's see the lemmatization. So lemmatization operates as a context aware linguistic scalpel. So for example, lemmatization have a dictionary or the part of speech tagging, and like for example, if we have input better, then it search and it look up into the dictionary and find the same meaning word like good, running, run. That is how it works. Lemmatization utilizes dictionary lookups and part of speech and tagging to recover the actual linguistic correct base word. And context matters, and it always try to preserve the context better good. That's how lemmatization works. The trade-off, while highly accurate and necessary for meaning preservation in complex language, it is computationally expensive and significantly slower than stemming. It is computationally expensive because it always search into the search or lookups and part of speech tagging. So it takes some time. That's why it is slower than the stemming. In the classical NLP, we have standard stop words like the, for, the, to, the. These are the stop words, and in the classical NLP, we just try to remove all those stop words and making the sentence more simpler. But removing these stop words can create or remove the contextual meaning and the relationship between two sentences, and that's why it is not efficient if we are just blindly removing the stop words. But in the modern LLMs, stop words are the most convenient feature for them to understand the relationship and the context about the words and the sentences. A linear model treated text as a bag of independent features, stop words, and added noise to sparse matrix, and were strictly removed to improve the signal to noise ratio. In the modern transformer rely on sequence and attention mechanism. So if we talk about the modern LLMs, and all the modern LLMs are based on the transformers, and transformer have the sequences and the attention mechanism. That's why it can focuses on the stop words and find the relationship between the words. That is how the modern LLMs works. But in the classical NLP, we remove the stop words to make it efficient in the processing. In the NLP, capitalization changes everything. So if we see a word apple, and if we see a word apple with a capital A, it means the company Apple. But if we see a word apple with a small a, it means it will have fruit. So aggressive lowercasing destroy name entity and alter fundamental meaning. On the fundamental meanings are really dependent on the capitalization, like US and US. If we write US both in capital letter, it means the country. But if we write US both in small letter, it means us. And the Polish. That's how capitalization changes everything. The systematic language bias of subword tokenization. Token cost for identical sentence meaning. In English, 10 tokens, but in Bengali. And in English, we can say a sentence and we can express a thought in 10 tokens, but in Bangladesh and Turkish, it takes 40 tokens. Because tokenization are really dependent on the languages. That's why in English it would take only 10 tokens, but in Bengali it would take 40 tokens. Tokenization is inherently inequitable across different writing systems. Processing text in languages like Bengali can cost over 4 times more than English, because their characters fractures into far more subword tokens. What is the real-time world impact? This density disparity creates severe latency issues for non-English users and drastically reduces the effective capacity of an LLM's context window. That's why the languages are really important if we are processing the tokens or processing the natural language. And it will always create trouble when we are processing the other language rather than English. NLTK provides, so there are two library in Python that supports the natural language processing. First is NLTK and the second is Spacey. Let's see the NLTK. The natural language toolkit prioritize explicit step by step text processing. NLTK supports a lot of functions that pre-process the natural language. Richer access to over 50 linguistic corpora and lexical resources provides multiple customizable tokenizers, stemmers, and taggers. And the use case ideal academic research, and NLTK basically is for the experimentation and the educational purposes and all things. But if we are going into the production environment, then we can't use and rely on the NLTK, because it is not for the production things. For that we need to use the Spacey library. Let's see the Spacey library. Spacey is an industrial powerhouse for production NLP. If we want to productionize any pre-processing and natural language thing, then we could use the Spacey. And it is 8x faster tokenization, built from the ground up efficiency and production readiness with core components written in memory managed C Python. Features a configuration driven workflow and an integrated pipeline that executes tokenization, post tagging, parsing, and NER in a single pass. And process up to 15,000 words per second on GPU standards. This is the power of Spacey library, and it is really efficient than the NLTK library. So if we want to use or something build build on the production level, then you can always go with the SPACY library. It is really amazing and powerful than the NLTK and other libraries. And this is the difference between the NLTK and the SPACY library. Environment, research and education, production and industrial. Speed, moderate, extremely fast, multi-step manual assembly, intricate single call pipeline, deep linguistic customization and massive corporate access. Speed, state of the art, accuracy and deep learning framework integration. The golden rule of modern text processing, pre-processing. Stay close. First, stay close as possible to the text distribution your model was pre-trained on. And the classical model requires aggressive normalization. Modern LLM require structural context and stripping away punctuation, casing, or functions. Tokenization and pre-processing are not just data cleaning courses; they are the lens through which your AI views the world. Let's go and see a pre-processing demo where we are doing some stuff that we had learned previously. In this NLP text pre-processing demo, we will going to see lowercasing, tokenization, stop word removal, stemming and lemmatization. These 5 things will go and see how we can do with help of the NLTK library. And if you want to perform this same task, then you could choose the specific library, but for the educational purposes and the experiments, we will always go with the NLTK libraries. So first, we just need to install the NLTK library, and after the installing the NLTK library, I have defined the text variable, and you can see some sentences are there in the text variable. So first we'll see how we can do lowercasing. So lowercasing is also important in our natural language processing. So that's just we need to use dot lower function of the Python to lowercasing these sentences, and you can see natural converts into the lower casing word, like with the small n. Here you can see the capital N, but here it is a small n. Now second, let's see the tokenization. So this is the English sentences. We can just use the regex pattern to tokenize the sentence. re.find all, and just we need to provide a regex, and with the help of the regex we are converting it into the list of strings. Third, we need to remove these stopwords, and let's see how we can remove these stopwords. And we are doing pre-processing of English language, that's why we have some set of stopwords. Just how we can do with some logics. So in the output you can see we are left with the words without the stopwords. In stemming, what is stemming? Stemming is blindly chop down the suffixes. Stemming reduces words to their root form by removing suffixes. Learning to learn, computers to compute. For that, we could use NLTK.stem Potter stemmer. Potter stemmer would help to stem a word, and for stemming, just we need to pass the word, and we are just using the list comprehension to process these things, and the natural become nature, language become language, and process remain same as it was, and allow remain same as it was. And let's see the lemmatization. For the lemmatization, we just need to download the WordNet and the stopwords lookup dictionaries. That's how it just look into this WordNet and the Stopwords and lemmatize the word, and the natural become the natural, and language processing. That's how. And if you want to create a function that do all those pre-processing part, then how you can convert and pre-processing all those things, and tokens, stamped and lemmatized tokens. In the conclusion, text processing is a critical step in NLP pipelines. It helps normalization text, reduce vocabulary size, improve model performance, remove noise data from data. That's how you can use the NLP and pre-process your natural language so that your machine or the machine learning algorithms can understand the natural language. Thank you.